This time slot obviously competes for your attention between the early flights, my presentation, and the bars. So should we call it a day, and go now to the bars? What do you say? All right, let's try to go through this. It's the end of the day. I'm Herminso Gomez from SAIS, and I'm here to talk about assessing rechargeable batteries with 3D X-ray inspection. And let me start with this question. What does the car shown in the picture have in common with a smartphone and a laptop computer? They all use rechargeable batteries as a power source, right? Today, rechargeable batteries play an essential role in a world that relies heavily on portable electronic devices. What is more, lithium-ion batteries have propelled recent developments and commercialization of electric vehicles to the point in which nearly every major automaker has announced a transition away from combustion engine cars to electric vehicles in the next 10 to 30 years. And there are several advanced techniques that can be used for inspecting rechargeable batteries. I'm going to use lithium-ion batteries as a reference for this presentation, but the very same principles apply for the purpose of inspection to solid-state batteries, which is the topic of this summit. For example, visible light, ultrasounds, X-rays, electron microscopes, neutron microscope, etc., are some of the inspection techniques that can be used. Some of them can certainly see inside of the battery, but there are some limitations due to the measuring resolution depending on the technique that you use and the penetration length. X-ray imaging is the only technique that can non-destructively see or assess the interior of battery cells across multiple length scales, from centimeters for cell level analysis to sub-millimeter volumes for a material microstructure analysis. And they capture relevant structural details with spatial resolutions that can range from several tens of micrometers down to tens of nanometers. And from the several types of X-ray imaging technologies, most of the industrial solutions for battery inspection are in the realm of the so-called macro-CT, micro-CT, and nano-CT technologies, or combinations of them, which is something that I want to emphasize in the workflows that I will present to you today. In the traditional CT X-ray systems, which are typically designed for non-destructive evaluation and industrial metrology tasks, the main approach is being to use a projection-based architecture. Those systems rely on geometrical magnification. But there are other types of instruments, the so-called X-ray microscopes, which include a set of lenses that add optical magnification capabilities on top of the geometrical magnification. And this allows achieving sub-micrometer resolutions with something that we call resolution at a distance to allow higher resolutions in the sample even when they are a larger size, because the ability to zoom into those samples with lenses or with the optical devices. This example shows how we can scan a full device, such as a smartphone, without destroying it. And then by zooming in with the lenses, we can scan small regions of interest, such as the smartphone battery, to look for any structural changes or degradation in different layers of the battery, such as cracks caused by fatigue, operation during several cycles of charging or discharging. And in this other example, you can see the image of an 18650 battery, where cracks and cracks around here and voids and imperfections in the internal structure of the battery can clearly be identified. And this level of contrast, of course, is exceptional when you compare to traditional flat panel images of simple X-ray computer tomography. So that's the additional advantage that you have when we use those optical lenses. In this image, different layers were segmented, of course, and you can do all kind of nice things like separate them and identify by colors and so forth, and identify the copper collectors, etc. But we could scan other types of batteries like the 21700, and I think this video you will see a 3D X-ray reconstruction of several portions of the battery using the concepts of resolution at a distance to scan smaller regions of interest at a higher resolution each time without slicing or cutting the battery. The battery was intact during the full operation. And several interesting details can be seen already from this video, such as the presence of particle inclusions in the different interlayers of the battery. And at the end, I think in the next one, you will see that we were able to detect a large crack inside of the battery, which was caused perhaps by a fatigue operation, and it is a rider coming in there. Again, all of this is a non-destructive technique, and this is what makes this technology very appealing, using the X-ray microscopes with a different set of lenses, because you can obtain different resolutions for different sections of the battery. The main idea of the workflow is that you can see an image of the full battery, and if something calls the attention, then you zoom in and scan, let's say, initially a 34 voxel size micrometer, and then start scanning at higher resolution 11.5, 4 micrometers, and 2 micrometer voxel size. You can see the details not only at high resolution, but also at high contrast. You can identify low density features in the battery, such as the polymer separator layer details and other details that, of course, you're more expert than me in batteries. I really, my expertise is on this technology. The so-called pouch batteries are also common in electronic devices, and this is automotive. There are larger form factors. This example, you can see how also using the different regions of interest, and in this case mean different lenses, the same battery can be scanned non-destructively to analyze different regions. And you see images there with the full flat panel, and also with the small regions of interest with the 0.4x lens, the 4x lens, and the 20x lens magnification. So the resolution at a distance basically enables you to do this reconstruction. And remember, though you are seeing 2D images, those are cross-sectional images, virtual cross-sections from a 3D image. You get the full 3D information. And that's the important thing here, because if you compare this to other technologies like electron microscopes, you actually have to section the battery to see, unless you keep sectioning and then you see multiple images and create an artificial 3D image. That's not something that happens here. And you can see now, if I show you this video, how you can see through all the different cross sections of the battery, because the 3D information is there. And you can see cathode and anode particles that are resorbable at high contrast imaging and reveal low densities features as well. And I think in this one, for example, you can, probably is in the one next, you can see, probably the next one, you can even see somewhere around here some bubbles. Well, it's on this section of the corner. And you can also see how you can overlap the different, because you have the information, the registration, the coordinate information in 3D space, and you can register one scan on top of the other to compare. And it's really impressive when you start zooming in to see the granular microstructure of the graphite anode in this case, as well as the mixture of lithium cobalt oxide in the cathode. You can notice all the microstructure on trails of delamination in this case. Of course, being able to see this after the structural evolution over time, you can then include these two studies of aging effects. This image shows typical changes in the microstructure of silicon particles of a graphite battery anode with aging. The silicon anode particles for these images can be identified by shape and contrast. I think in the first image, the bright ones. And after aging 200 cycles, we can see that the silicon is almost completely gone. So what happened in between? So if we scan now an intermediate step, let's say 100 charging cycles, then you can see that we see that at that point, those particles, the silicon particles start to crack and they are pushed away around it. So it disappear after several 200 cycles. And these are, again, very interesting information that you can observe non-destructively in the battery. Now, if you want to go to higher resolution, there are some limitations on size. If you go to nanotomography, in which actually you have to slice a portion of the battery, still you're doing non-destructive of that portion. You don't have to slice phase by phase. And then in this case, you can see what is happening in the same example, but in 3D. And you can do other types of studies. It's not only about aging. Well, yeah, certainly aging, but you can see some morphological deformation in the edges of the electrodes, stress formation, some variation of the radial distance, and separation of the different interlayers of the battery, which is certainly very important for you. And we can also check the outcome of poor mixing and weak battery compaction process. The two cathodes shown in the video have been compressed at different calendering pressures, resulting in differences of density of the particle packing and porosity of the electrode. So potentially affecting the electrochemical performance of the battery cells. You clearly know the low pressure canderings lead to cathode particles that are separated too far apart and with voids in the binder material. This will be reflected in suboptimal energy density or poor charge capacity of the battery. And you can see the particles, the surface degradation, and some of the cracking in this image, which if you want to do further analysis, again, the data, you already have the data in gray levels, but you can bring this into a software to do more analysis and get some of the images of the different types of sizes of the particles and even see some of the dendrite structure. And those fine details, then you definitely need to do something that is called nano computer tomography to see nanometer resolutions. And you will see a small portion in this case, and you will need some sample preparation. And if you want to keep doing analysis, you could do some kind of put this data into a simulation model to see some simulation of structural, mechanical structural channeling inside of the battery. And I could continue giving you examples, but I prefer to give you some very nice references in which you can see how you can take advantage of this type of technologies. This is a nice article published in Nature Communications in April 2020, which shows a CT scan of an 8650 battery and then very fine details obtained with 126 nanometers and even a 63 nanometer voxel size right there with one of our size ultra X-ray microscopes. And there is also an SEM image just for comparison to see the level of information. Again, this was a slice in the battery that was a real 3D image, and what you see is a cross-section. And there is this one also that was published in Nature Energy, which you're free to read and learn more about what you can learn with this technology on your batteries. We did, given that technology is evolving and also the improvement that we have done in technology, including some artificial intelligence or deep learning algorithms for doing the reconstruction and improving the scan time. I will say, if you check this paper, it's a nice reference that we publish as an open access. So you can learn basically in details what I've been telling you in this conference. The X-ray quality assurance solutions that we can provide is go from checking the anode, the cathode, the separator, the raw materials, the electrode production, the cell assembly, the module assembly, and the battery packs to check the foil stacking, welding joints, or contacts in a non-destructive manner. And of course, you might need different types of X-ray technologies, ones with have more power to do higher penetration. If you want to see higher resolution, then you have to use the lenses or things like that. But the idea is that the technology is overall capable of doing that. Of course, at some point you will hit the limitations. The limitations for the way the X-ray operates are basically penetration lengths, the X-rays. What you capture in the detector is a signal, which is the attenuation of the X-rays when they pass through the sample. So that signal depends on two main factors: the density of the material and the thickness of the sample. So if you go to battery packs, you will need more X-ray energy to penetrate those battery packs. And your resolution will be somewhat limited. You cannot think of getting nano resolutions on those type of samples, because there is a trade-off between those two, power source and the resolution. And so this is an example for battery cells and battery packs, in which you can see that with X-rays you can check for things like overhanging measurements or metal inclusions, cell defect, welding defects, electronic components quality, delamination, deflected anodes, voids, and housing integrity. So that way you can kind of close the cycle at the research laboratory, at line production, both for quality inspection and failure analysis. For inline production, certainly the technology will bring some challenges in terms of the scan time, because the scan time can need to be reduced to under 1 minute. And that's certainly possible with some types of X-ray systems, but then you compromise things like resolution or quality of the data. So it's a nice thing to have, but it's not as easy to implement. Just let me say that upfront. For inline production. So it's more of a kind of a sampling or at line when you take the samples and you do some analysis. So these are the typical markets that we serve. Of course, automotive, aerospace, medical devices, electronics, and batteries, including solid state and lithium-ion batteries for electronic vehicles, energy storage, and consumer electronics. And all of these 3D X-ray microscopes that I've been mentioning today are part of a larger multiscale correlative microscopy tools, which include microscopes capable of delivering spatial resolutions down to 0.5 nanometer with the helium-ion microscopes. And the nice thing is that because we have the coordinate system in which we bring the data into the software, we can correlate them. And that's a nice thing to have to this is very challenging for people that try to use an electron microscope and they don't know actually where to see. It's like looking for a very small detail in a big sample. So this correlative microscopy is certainly going to help to do these investigations. That's how we can get the multiscale correlative insights into batteries by combining X-ray microscopy, computer tomography, and other microscopy tools, such as electron microscopes. This is, of course, when you go to electron microscopes, then you're doing some type of destructive testing, but in principle, you could take advantage of the non-destructive imaging capabilities of X-rays from centimeters to nanometers if you select your right system. If you want to go down to electron microscopes, then it's up to you. When you really need to go down to like 1 nanometer type of resolution or so. And just to mention, I've been focusing on X-rays and microscopy, but there are other tools, of course, when it comes to dimensional analysis, which there was a talk about that today. In the large scale, when you are doing battery packs, then people use coordinate measurement systems or CMMs and other type, or laser scanners to do surface reconstruction or something of the welding of the battery. Just to add to this, the pocket of tools that you could use. And with that, I like to finish here, and I'll be happy to answer any questions you might have.
All right, thank you very much. I was hoping for some cool videos, and I was not disappointed. Any questions from the audience? Yeah, one in the front here.
I'll go there.
Oh, you'll head up? Okay.
Christian Ullmann from Steel. Thanks a lot for the interesting talk. I would like to ask, how long does a scan with the X-ray microscopy takes for, let me say, one 18650 or 21700 cell in high resolution? How much time is it?
Yeah. So if you remember the image where you had the 1800 battery, if you get the full battery, you can get that in half an hour or less. But now if you want to get higher resolution, we're talking in the order of 1 hour or more. If you go down to, let's say, use the 20x lens, you're talking something 3 hours or more. Now, we are improving those times with something I did briefly mention, which is deep learning. The way X-ray computer tomography works, which is the same technology you use when you go to see the doctor and they put inside of a machine, is you have to collect a set of different images. And the traditional reconstruction algorithm that for industrial purposes people have been using is called Feldkamp or FTK. It was invented in the 1980s by some gentlemen working at Ford at that time. And it is great because it allows you to do the reconstruction with a cone beam. You only need to do a rotation, and that's good. The disadvantage is you need to use a large number of projections. So you need to rotate the sample and collect images more than 1,000 projections. It's 2,000 or 3,000 is something regular that you can you need for high quality. When you start reducing the number of projections, then you suffer of something that is called aliasing, which is basically undersampling. And the way that we figure out we can get away by reducing the number of projections and not affecting the image quality is by using deep learning. And what you do is you take a sample that you are regular samples that you're scanning, and you scan the first one at a high quality, and you use that data as a training base. And because you have a bunch of the virtual images slices, you only need a scan. I mean, deep learning needs a lot of data, but in reality, you have a lot of data already. And then you take that and train the software such that when you do the second scan or the others, you use your model and you can reduce the number of projections from the thousands to hundreds. We've seen throughput improvement in the order of 4x, 6, and up to 10x for batteries. I don't have images, but I can send you images of those. That means that we have ways to improve the throughput in those cases.
I think there was a second question also somewhere in the front. No, maybe not.
It seems like you want to go now.
There you go.
Yeah.
So, sorry, I didn't hear the question.
I'm sorry, stupid question. How much does it cost such system?
You're talking about several hundreds of 100K, or easily can get to 1 million or 1.5 million, depending on the system you configure. But I will say the base system that you can find in market is in the order of 500K, 500,000. And then it keeps going up depending on what you add. You can certainly find cheaper systems in the market that can do 2D without the computer tomography capabilities. And that we're talking about 200K or something like that. But the problem, especially with batteries, is that with radiography itself, it's very hard to see what's going on inside in the layers because everything is overposed. It's probably a good technology if you only want to do overhang measurements, like check the alignment of the electrodes, because you can easily see that in a pouch battery, for example, you can put it in the system. You don't need to rotate the sample, and you can see the electrodes overhang.